Online. I'm Courtney Roberts, and it's day 2, Friday. We're in the middle of our sessions on what could possibly go wrong, and so far everything's gone pretty well, actually. Our next speaker is Jagdish Maheshri. He's in Houston, Texas, and he's going to be speaking on a fascinating project that he's been working on for many years now, and it's an earthquake prediction model. Just a little bit about Jagdish. He is a contemporary Vedic astrologer. He's got a PhD, and he was for many years the research director of NCGR and has published extensively in their journal and spoken at astrology conferences and events all over the world. So I'm sure you're going to really enjoy what he's got to share with us. So without any further ado, take it away.
Thank you, Courtney. Good.
Yep, sounds good.
Okay, sorry.
Screen share. Okay, there you
go. Good afternoon, everybody. I'll be talking about my ongoing research. It's the earthquake prediction model. There were model 1, 2, 3, actually 4, and 3A. But I'll be talking about the model 3, which has been working pretty good so far. Yeah, I want to say before I begin, any one of you can jump in anytime if you have a question. And I would try to answer as much as possible. Okay, why earthquake research? First of all, it saves life. If you have advanced warning, it definitely can save lives. It promotes, protects, and enhances the world economy because there is less destruction. And why am I doing the research on earthquake? Because I get the most accurate data. Because as you know, for any research, data is very important. And accuracy of the data is the vital to any successful research. Okay, well, for this particular model, or for any other models also, I'm exploring the correlations between planetary data and earthquakes of magnitude 7 and higher. Why 7 or higher? Because earthquake occurs pretty much every day. The earthquakes of magnitude 4 or 5, every day you have a couple of those. 6 and higher, it's about 10 a month. But 7 or higher, about a month, or I mean, once a month, or about 15, on average, 15 a year. And so because I was more interested, or I'm more interested in predicting the dates. And so if I have 10, it's my, what I call is the success of the model, because it's measured by statistical p-value. And so if you have if you can narrow it down to few days, the success of the model goes up. And the intended goal is to predict future earthquakes with a greater advance warning, as I mentioned earlier. And I will be presenting in a summary fashion the results of my model 3 for 6 years. Okay, there are there's a training set, what I call is a training set, on which the model is based, is based on 110 years, beginning 1900 to 2009. And using that data, I have come up with this model. And then I'm applying the model for the prediction, which is I'm applying for the future. And so here are the results beginning 2011 to 16 that I will be presenting soon. But as you know, occurrence of earthquake is a random event, and earthquakes may depend upon, and this model assumes, this is the assumption here, or hypothesis if you want to call it, depends upon the geocentric longitudinal planetary positions along the ecliptic as viewed from the Earth, which are basically, most of us are astrologers. So basically, these are longitudinal positions of the planets that we use mostly in our charts. Now, regardless of the system you use, whether it's a tropical or zodiac, I mean the sidereal, I'm really interested in the angle, in the difference between two planetary positions. So the result would be identical in either case. Okay, along the basis, as you know, angles between every planetary pair, and angle between two planets is the same, as I mentioned, yeah. And then for this model 1 and 2, they were based on the multiples of 15 and 12 degree angles. And I really didn't have very satisfactory correlations with those two models. And then I can see that, in hindsight, I could see that why. For the model 3, what I thought is, why am I focused on certain angles? Because I'm an astrologer, and so I already have a bias about certain things. So I said, let's start. I assume myself not an astrologer, just a researcher here, and see what see if I can look at the data and do I get any insight? And what I found, then I thought for a second, what if I use the angles which already occurred more frequently than other angles? Maybe I could have some success, and lo and behold, my R-squared value, which is the measure of the correlations, it went up to 0.3 to 0.55. Okay. Now, the most important in this model, any research work, as you know, most important thing is we have to understand the assumptions we make and the limitations we use for the model. And so, because that's the starting point. If you don't have those, then you're going to get lost. So you have to restrict, and then slowly, one by one, unrestrict those restrictions. So, okay, what I found is the more the number of angles, the higher the severity of the earthquakes. So if earthquake of point, but okay, and then every planetary angle pairs exerts a unique influence on earthquake magnitude, and therefore weighing of planetary pair angle becomes necessary. This is more important than the first one. In other words, you could have 2 or 3 number of angles, but you could have a very high magnitude of earthquake because the planetary angles that were involved with respect to that high magnitude earthquake has a higher weightage. And so this weighted model is developed using a simple linear regression technique. And so here is the basic assumption is I'm assuming that my earthquake is a function, or it depends on all the planetary angles in a linear fashion. As it turns out, as you know, the earthquake of magnitude, say if you go from 6 to 7, it's a 10-fold, 7 to 8, further 10-fold. So it's not really linear. But I have to assume linear because I tried to apply nonlinear models and I just didn't have any success. At this point, I'm thinking, well, how far can I go with this model? But this is a serious limitation of this model. Okay, I'm using 6 outer planets, 2 inner planets, as you know. 6 outer is Uranus, Neptune, Pluto, and Mars, Jupiter, Saturn. 2 inner, Mercury, Venus. Then Sun, Moon, and the lunar node, or North lunar node, which is in Vedic astrology called Rahu. And each of these, okay, so there are these if you take these 11 planets, so you get 55 different pairs. And for each pair, I'm using the 16 most frequently occurred angles. In the past, on the training set, which is from 1900 to 2009. Thus, we have 880 maximum possible unique variables. Now, the moon's average daily variation, as you know, is almost 12 times faster than the average, the inner planets and sun. And so what happens in a 24-hour period, because I'm predicting only a day, date. And so it's a 24-hour period, moon sweeps through about 12 to 13 degrees. And therefore, it may not be, you may get lot more angles, or it just repeats those angles, maybe. But nonetheless, I use both cases with the moon and without moon when I develop the models. So this is the mathematical representation of the model. So my magnitude is a function of, which is 880 angle pairs. And this Cn is the weighted average for each pair. And then, of course, the constant, because it's a linear equation. And when that angle hits one of those my 16 frequently occurred angles, then this angle pair becomes 1, and then otherwise it's 0. And so that's how the equation is. Now, for any earthquake, I'm not going to have more than about 10 angles, because there are only 11 planets. And so mathematically, there are only, when I take the angles from out of 11 planets, there are 10 unique angles. In other words, what I call is independent angles. Remember that this angle pair is supposed to be independent in this equation. And so that is one of the challenge in this particular thing, because you could have, for any given earthquake, you always have 55 angles, but you have to pick up no more than 10 out of those, because those are the independent and others are a dependent model. Because just imagine all these 55 angles comes from the information of 11 planetary data. So you cannot have more than 10, because then what degree of freedom they call it, if you go from planetary data to angles, is reduced by 1, so you have 10. Anyway, so going to the next slide. Okay, the orb I'm using is half a degree. Let's just say my frequently occurred angle, one of the 16s, is say 33 degrees. So my orb, so between 32.5 and 33.5, if that angle occurs, then it becomes unity. And I include that in my analysis. Okay, the linear regression was performed and the coefficients were estimated by generalized least squares. Now I have, for this model 3, I have 4 sets of model, or you can call it subsets. 880 variables, which is all variables included. 720 is when I remove the moon out of those 11 planets. Then 410 is if I took 880, and then I'm saying, okay, I'm going to be looking at all these coefficients that I obtained using 880 variables. And then there are some coefficients were insignificant. Their influence on the model was extremely, it was just negligible. And so using the criteria, which is t is equal to 1, which is the measure of the significance of the significant influence on the model. And so I use t is equal to 1, which gives me, so I'm just keeping the one which which is based on that criteria, t equal to 1 and higher. And so that gave me 410 variables. Basically, I removed 880 minus 410 variables. And same thing I did for the no moon model, which is from 720 to 280 variables. And now, as I mentioned, I'm using only the data points which were 7 and higher for 110 years. So you can see that average is about 15. Now the limitations model apply over a narrow range of magnitude. It is based on that 1672 data points, and the R-square term, it varies from 0.4 to 0.53. Again, I'm saying indicating a not so perfect fit. For perfect fit, you really have to go above 0.7, 0.75. But even nonetheless, directionally, it gives me a pretty good, directionally it's pretty good, I would say that. And the requirement of the minimum number of angles. If there's a 0 angle, I just ignore that. And actually the minimum is really the average for that year. So if I look at 2013 year 2013, apply for that year, whatever the average number of angles. So I have to meet that condition, which is the minimum is, at least minimum has to be the average. And there will be some exceptions for that, but that's the model. This is the way I have developed the model. Oh, okay. Let me go. Okay, I have to, Courtney, I have to change to the other slide. How do I go back? Okay, escape. Sorry.
Yeah, you're doing fine, Jagdish. Okay. So make sure what you want to show is at the top of your desktop.
Yeah, okay.
And then when it brings up that little window, choose it, okay? And while you do that, I'm going to read a couple of the comments, and I think there's one question. First comments was Renee chimed in right away saying log linear, no problem, no limitation.
Yeah,
she likes that.
Yeah.
Okay,
right.
And then Vince,
I tried that, and I didn't have a whole lot of success there.
Okay, then Vincent says, the idea of no more than 10 to preserve independence of variable is brilliant.
Yeah.
Okay.
Yeah, that's
all
awesome.
Right. Then when you got to the R, Renee chimed in again. She said, that is a great R.
Yeah, right.
Okay, and then you have a question from Linda, who just chimed in here, and she says, so you only included earthquakes that had a minimum number of angles. That's her question?
Yeah. No, wait. You are talking about training set, or you're talking about prediction? That's the question. Okay. I'm a little last year. I got to get the screen, but give me a 10. I'm not a multitasker, so you have to.
Yeah, and she was talking about the last slide. Don't worry, take your time. I know it's complex stuff. She says, I'm talking about the last slide.
Oh, last slide. Okay, the limit. Okay, yeah. A requirement of the minimum number of angles. If it is, say, the average for the, say, when in the training set, the average of course, these are training set. All Earth, I'm using the points which are 7 and higher. And so I have what I call is the average is about 9. Depends on which model. For 880 model, its average is 9. Average is 7. 9 was the highest. 10 was the highest. The average was 7. Now, if I look at the date, say 2011. So I have to look at all the dates. I don't know which date is going to occur. So for all the dates, the average comes out to be somewhere around 3, 3 1/4, 3 1/2, sometimes 2 1/2, something like that. Okay. But in the training set, which is the model itself, sometimes I can have 3. Number of minimum angles can be 3 there. The minimum was about 3. Average was 6, about 6. So 3. But then when I look at the weighted average, wow, that's where it comes from. Those coefficients. Where you do the weigh. So that's where it comes from. I try to I'm not very, successful in reconciling that when it comes to prediction. And so that's why my predictions are not like perfect predictions. No, absolutely not. Even if I get, and I will show that slide, the predictions, how I did it over 6 years. And, it will become clear.
Okay. Yeah, Linda says thank you. And Vincent just has a comment here. He says this approach with 0 to 1 for angles instead of using orbs confirms my own experience with this type of model.
Yeah, okay. Well, thank you.
Okay. All right.
Now, I need to go back here. I don't know, I'm lost, but let me bring that.
Start screen share.
Okay, let's see.
That should be down at the bottom in the middle. You click screen share.
I think, okay. Post that. It's a sign, start at the bottom.
There should be a little icon that says share screen.
No, but I'm not going there. Okay, all right, okay. Share screen.
Uh-huh. Okay. And then it'll open up a little menu and make sure you choose the thing you want to show.
Right.
Yeah.
Right, okay.
And then you click on that.
I have to go to the desktop first to bring it on my desktop.
Yeah.
So how do I, so if, can I leave this screen and then go to the?
Sure, click your desktop, click something on your desktop and it'll bring it up.
Okay.
The Zoom screen shows on your bottom menu as a round circle, a round blue circle.
Okay, yeah, I got it. Okay. Let's,
if you want to go back to the Zoom window, you click on the circle.
Okay, I know. Okay, it's an Excel file. Okay.
Do you want to describe?
Okay, yeah.
Okay, you got it?
I'm there. Yeah, I got it.
Okay.
Can you see my screen or not yet?
No, not yet. You haven't hit share screen yet.
I'm on the desktop now. Okay, now I go
back into Zoom, click that little blue circle with the camera in it, and it'll take you back to the Zoom window.
Okay, yeah. And then share screen?
Share screen.
Okay. Then got it.
Choose the thing you want to show.
Okay.
All right. Now we're getting there.
Sorry about that. Okay.
All right.
Okay. Now what I have is a table. There are a table for each year. And in the first column, this is the months for, January through December 2011. The second column is the actual dates. So you can see the January 1st, January 2nd, 13th, and in the parentheses is the magnitude, 7, 7.2, and so on. Now the prediction dates. So there are 16 dates that I chose for January. The model chose, not I didn't choose, the model chose. And so out of those, so those are listed here. And so there were, okay, let's see. How do I get? I see the pictures covering the screen. Okay. So there are 4 hits. So there were 18. So there are 4. I predicted, it happens that the model predicted all 4. But it had to use the 16 days. So only the 4 day, so basically using 16 days out of 31 days, the model successfully predicted all the hits and so on. And then, so the last 2 columns is number of days for that month I chose. And there are the hits. For example, in the March, there were 2 earthquakes. And out of that, this model predicted 1 and so on. So there were 120 days, choosing 120 days. I had 13 hits, I think out of 16 or something. So for each, okay, the red ones are the one where the prediction dates match the actual dates. Then the model, you can see 2012. It didn't do so well. You can have 6 here, 2012. For example, in March, there were 2. I chose 14, the model chose 14 days and it hit 1. Here there were, there was 2, didn't make it, and so on. There were none, none, none. So this is interesting. See how, this is what I like about this model is, okay, it didn't choose the lot of days when it didn't occur. So directionally, it's pretty good. Well, I'm boasting myself. Okay. There's the next one, 6. Okay, 6 out of using 104 days, get the 6, and so on. Then the 2013, 2014, I got 8. 2014 was pretty good year, 11. 2015, 4. But there were only, yeah, this was not a good year for that model. Then 2016, 6, and so on. Now, if I summarize these, okay, so this is where the summary is. The first column, years. Second column, prediction dates. You know, that comes, for example, 120 and 13 from here. The number of earthquakes were 17. And so P days is nothing but number of days divided by 365 or 366, depending on the leap year. And this is the binomial probability. You can use the Poisson, it gives the same type of probability. So what it shows, you know, this is the one here, my p-value, this is the p-value, the last column, is using 120 days out of 365 days, the model has successfully hit 13 out of 17 earthquakes. So the probability of this, you know, for this particular year is 0.0002, which is like 0.02%. Basically, what it means is to successfully hit 13 or higher number of earthquakes out of 17, the probability using 120 days out of 365, the model, the p-value is, or the probability is 0.0002. Actually 3, you know, close to 3, but anyway. And then for each year, you can see that 212, not so good, but still better than the random, you know, if randomly you select the dates, which gives close to 0.9. So it's still better. Then the 2014, it does pretty good. 2015 was the worst, 4 out of 17. 2016, 0.09. But if I combine all of these, I get, I'm using 40 successful hits out of 92, using 738 days out of, I think, 2100 something. The probability comes out to be, or p-value, 0.0001. That's all. Okay. Wait a minute. Then this is, I also have the results for model 3. Let's see this on the, I have to go back. Can I stay in the share, this same screen, but change the desktop? No, I cannot do that. No?
Well,
okay, I can quickly do that. I was trying to show, I have the model 4. Maybe I shouldn't do that. Maybe I will confuse the people. That's fine. I think I'm, unless, okay, yeah. I think my presentation is, now I'm open for questions.
Well, thank you. And I think Linda had a question. She's saying, which model is which. I think she's a little confused on, and Linda, maybe you could clarify that a little bit. While we're waiting to hear back from Linda on that, Renee is saying, I don't think you can add p-values, maybe average them?
No, I'm not adding them. I'm not adding them. So if I go back to my screen share, desktop.
Hey, now you're getting really fast at it.
Yeah. Getting hang of it. Okay, yeah. Now these are yearly, but I'm not adding these. I'm using this number. I have 48 hits. I have 92 earthquakes. I'm using 738 days out of something like 2100. Let's see, here is, okay, 365 times 6 plus 2, whatever that number is. I'm using that. So this is all independent. I'm not adding this. And this is, so I'm using K22 is 48, then 92. M22 is this, which is 1/3, usually it's 1/3. 738 divided by 21 something gives me 1/3. And that gives me this probability.
Okay, thank you. Linda has clarified her question. She's saying he showed data for model 1, model 2, and model 3, which was with or without the moon. So she's asking, was one of your models more successful than others?
Excellent question. I forgot about that. Okay, now the model that I'm using here is the combination of two models, which is 410 variable models, which is kind of, I'm removing the noise from 880 model, come up with 410. And then I'm using the no moon model. Because problem with the moon is when I do the prediction, I do the prediction for the noon of that day, GMT. So I don't have the luxury unless I run, my simulations for every hour or every minute or whatever. So what I'm going to do, so basically I lose some of my training set is based on the accurate moon position because I have that date, time, everything. So training set is perfect. The model is perfect. But when I apply, for the future prediction, I use the noon time. And so then I thought that, wait a minute, let me remove the moon first. So whatever I get, so that's the one which is 720 model, which I believe, which is good, but I don't have the moon there. And I know moon has important influence. And then I'm using the one where I'm removing the noise, which is 410 watt, and combining them. And then I'm looking at combinations. So there is overlap. And so I'm using, so basically when I combine, this is what I get. And then 20 days. If I just use, say, model either 410 or 720, then these days would be something like 80 and 80, 85, something like that. Range is 80 to 90. But then because of the overlap, there's considerable overlap, the total is 120.
Okay, we're getting a lot of interesting comments and questions, and I'm going to try to go through them in some kind of logical order because this could get confusing. Vincent is adding a comment, I think, as a follow-up to what you just said. And he's saying, maybe adding midpoints, which are variables of the same nature than aspects, in your regression model could improve it a little.
Could you please repeat that?
Yeah, he's saying maybe adding midpoints, parentheses, which are variables of the same nature, maybe adding midpoints in your regression model could improve it a little.
Adding the midpoints?
Maybe.
Okay, that's a good point. Yeah, good.
Okay. Yeah. And yeah, he was just following up there. Now, I wanted to go to Scott Silverman's questions because apparently he's been reading your stuff. And he's asking, weren't you using declinations as well? And didn't that add a major statistical bump?
A wonderful question. Okay, this is where my model 4 is about. Okay, what I did is, I like to take a walk and look at the skies, and when I see that, when I see the planets and when I see the say conjunction, on the longitudinal way, but then planets are not exactly on the top of each other; they are away, and so that's because of the declination of those planets. So I thought that what if I take, declination must have some influence on that one. So what if I look at the declination? I try to look at the both declination and the longitude in a combination ways. But that was a huge, that was too complex for it was too complex. So then I said, I'm just going to be looking at the declination and based on that, see what I find. And as a result, I had, which is, as a result of that, I published a paper on Model 4. Now, on the declination part, I didn't have the whole lot of success as I had with the longitudinal. But same number of models, everything, but I'm using the declination there. Same 11 planets. I'm sorry, I don't have the Rahu there. So, no lunar nodes in declinations. So, yes, I had 10. But there are two sets of models. Then what I did is, because it's very difficult to decipher the dependent variables, especially when it comes to declinations, so I use the sun-based models. Basically, when I'm saying the pairing all planets with the sun, so sun, moon, sun, Pluto, sun, and so on. So that removes that ambiguity of independent variable, and that's how I developed that model. And that had some success. Overall, I would say p-value was 0.09 or something that came out there. So I presented that, even though it didn't. So I compared against the Model 3, and so that's the Model 4. And then another paper which is coming out in February, which is going to be published in AFA Research Journal, which is Model 3A. In Model 3A, what I'm doing is basically, the way I'm, it's basically about how I remove the dependent variables, because, it's not easy job to figure out which one. You see, for example, there are 3 planets, A, B, and C. So the angle between, once I know angle between A and B and C, then I know the third angle, A and C. I don't need to know that, because I'm using three planets and removing 1 degree of freedom. I have 2 independent variables, and that's the reason I have 3. So the third one, which one you remove, either A minus B or A minus C or B minus C, which one would you remove? And so that is the part where I'm still hassling with that, because I have to use the same criteria. One of the criteria I use is I'm going to remove the pair which has got the slowest moving planet. So because I think that, this intuitively, I think that the farther the planet of, the planet, the less the influence, but that's really, I'm not so sure about that. Have I answered the question?
Yeah, and I mean, that's a good point. I wouldn't just assume the farther, the less, until it was actually tested. We're getting some really good questions here. First, Scott says, thank you for clarifying. And then Inessa had a really good question. She says, are earthquakes random?
Right.
In other words, I thought that earthquakes often have follow-up earthquakes.
Correct.
So,
correct.
Yeah.
That's a good question. So one of the things I did in my training set, suppose if the earthquake occurred and then you have a follow-up earthquakes. So usually follow-ups occurs on that day. Usually, I'm not saying it does, but if it occurs on that day, I'm using the highest one, and I'm not using other ones for that day.
Okay, fair enough. And we have another question from Mary. And she wants to know, were there specific angles or planetary combinations
Excellent.
that showed up as a significant?
Excellent questions. Well, first of all, let me make a blank statement that there is not a whole lot of dependence on our conventional way of looking at it, is like specific like trines as opposed to quincunxes and squares or so on. I didn't find that. They were quite random. They were random. Only thing I noticed while I'm observing all these different models, that Mercury, when the speed of the Mercury is very close to the speed of the sun, or rather the Earth around the sun, the same speed, which occurs around 18, when the Mercury is about 18 degrees away from the sun. Around that time, like most of the earthquakes occur, the significant magnitude. That doesn't mean for every 18 you have earthquake. But if you look at the earthquake data, you will see that you will see the significance of this 18 degrees. They tend to occur around 18. Of course, there are some earthquakes which are away from 18, but within 17 and a half and 18 and a half for the Mercury. So this is what I call, that they call it some phase, Mercury has it goes on the flanges, which is like 27 degrees away from the sun. And, and then, it comes back. So retrograde and direct motion, when it comes around 18, there's a chance. And for Venus, it's on the flanges, which is meaning it's a 47 degrees, 47, 48, I would say more than 50. So, you will see that the chances of occurring earthquakes on those times are, significant in the sense that it's compared to other times. But there are other planets also influenced, but I did not find any significant things. That's one other thing I will be looking at once I get some handle on this one. This is kind of a lifelong project. It just, it goes on and on. I don't have a whole lot of time to spend, but whenever I can, I spend it. But I end up spending quite a bit anyway.
Well, now, Jagdish, I tried to warn you about these people, okay? They're good. They're good. Now, Scott has another comment referring back to the earlier discussion on the possibility of introducing midpoints. And he says that the Uranus-Admetos midpoint, according to Diana Rosenberg's research, was significant in her earthquake study from a generation ago. So he's just, putting that out there for your consideration. At the same time, Vincent has a proper question. And Vincent, who's always got interesting questions, says all your models are built with the same data before 2011. That's a question. Are all your models built with the same data before 2011?
Up to 2009. So 2009. I don't have, but I'm applying, 2010, I didn't, I don't know why I didn't do that. I thought to start with the next decade or something. I don't know, maybe. But 2011 to 16, I tried that.
Okay. And
no, I think perhaps the reason is 2010, I was using the old, that's right. 2011, the reason is because I wasn't using the earthquake model 3. I was using model 1 and 2. And
why don't you back out of your screen share for a minute, and we can get some interesting video going, because we've got some good questions for you, Jagdish.
Sure. How do stop share, right?
Stop share, yeah. Mm-hmm.
Okay, got it.
There you go. There you go. All right. So Anessa followed up Vincent with this question. She says, which planets or angles did you weigh the most? Meaning, which planets or angles are most strongly correlated to earthquakes?
Okay. That reminds me, there is another slide, I have to go back?
Oh, yeah, you can. Absolutely. Okay. Absolutely.
How do I?
Screen share. See. Make sure it's on the top of your desktop before you hit screen share. Right. Okay.
Oh, I got to go. Okay. And I don't have top of the desktop. How do I do that? Let's see.
Yeah. Click on something from your desktop to get
be
on the Zoom. Now click on that little round blue circle with the camera in it to get back into Zoom.
Okay. Yeah.
And now go to screen share.
Microsoft Excel. All right. Okay. You see this screen?
Hang on, it's opening up.
Oh,
Okay, yeah,
okay.
now there's a spreadsheet.
Okay, now this is a 410 variable with moon model. Now on the column B, the first column are the pairs. So say Pluto, Neptune, Pluto, Uranus, Pluto, Saturn. And these are 1 through 16. So 1 through 16, you see that there are some holes because it's a 400. I removed those other variables which were not significant. So you can see 0.09, 0.06, minus 0.12 for Pluto-Neptune pair. So the one that Mercury, say Mercury and Sun, this is, for example. So yeah, Mercury, Sun, 0.07, 0.07, 0.09. And then if I use the one with the moon, it's a little different. But, so these are the ones. So basically, these are the ones. So you can see that they vary. I think it's 0.26 is here. Jupiter, Mars, 0.26. I think the highest I remember, 0.3, this 0.34, not over 0.4 or something. But this is what. But I tend to keep anything below, anything above 0.04. So you can see that because the t is equal to 1 is close to that.
Okay. All right. And then Doug Egan says, I'm not a fan of using gravity to explain astrology, but in this case, wouldn't it be important to take gravity of the moon into account more for prediction? Have scientific studies implicated the moon's gravity as a trigger for earthquakes?
I spent about 8 months just looking at, okay, I'm going to be looking at no planets, nothing, just the Earth, moon. Basically, Earth's orbit around the sun and the moon's orbits around the Earth, because these are the really important forces. And so I looked at basically acceleration, velocity, and of course, using that Einstein equation, m1, m2 divided by the distance square. And so I'm using like Earth. I have the mass of the Earth, mass of the moon, mass of the sun. And based on that, but I didn't have I had some success, I can say that. But compared to Model 3, it was nowhere near. But that's
okay.
That's a good question.
No, I mean, it's a very interesting question.
Maybe I'm missing something. I want, others to kind of take a lead in that direction. I would like to see many people taking interest in this, and then we can really do something. We can really go someplace.
Well, Scott's very interested because he's back with another question/comment. He says, have you attempted to address your research to astrocartographic mapping techniques and maybe attempt to predict where the earthquake will happen?
That is the next step. Well, I have some ideas at this point, but I'm really, I like to wait till I improve this model to a point. I feel if I can get something like 60 to 70% of the earthquake with third of the days of the year, then I think I'm ready for that. Because unless I clear this up, this is the foundation, then I can look at because there are regions over which earthquakes occur. There are because it depends on the plates. There are about 22, 23 regions around the Earth.
Right, so it's not just random,
Right. Yeah, so then what I have to do is, then I can go back to my, once I have better handle on this model, if I get 70%, 75% out of 1/3 dates, which gives me probability pretty good, then I can go and see, okay, which planetary angle pairs are important for this region as opposed to the other region. And then I will have really good insight. And then I can, this is my thinking at this point.
Mm-hmm. Demi's got her hand raised, so I am going to just promote her right now and get her
Sure.
mic opened up.
Sure.
Okay, and here we go. Yeah, I think I've got her mic opened up.
Still muted.
And I'm sending her a thing to start her video as well. Yeah, Demi, I'm having a little trouble unmuting your mic. If you can see your mic icon in the bottom left of your screen, it's got a red stripe across it. Just click on it so we can turn your mic on. Because I'm trying to do it from here. And okay, here you are. Hello, Demi. All right, I'm gonna take her back out because that doesn't seem to be working on that. We've got plenty more questions though, okay? And Kenneth again is asking, see, they're focusing on the where, you know, and he said, I might have missed this about, are you able to predict where? So I think you kind of just, you know, covered that one, okay? And then now, this is a question from Manda. She's asking for a little follow-up on the name of the astrologer. It's Diana Rosenberg, I believe, that Scott mentioned earlier. And the midpoint was, Scott, if you want to type that back in to help out Manda there. The question for you from Vincent, Jagdish, is, are the scores in the sheet correlations? That's what Vincent is asking. In other words, the scores in your spreadsheets there, are those based on correlations?
That's right, exactly. This is the training. This is the training set, exactly.
Okay, very good.
This is the basically, for example, just to give an example, if I take this, can you see my screen?
Yeah, yeah.
Okay, okay. So say Jupiter, Mars. This is 0.09. This is whatever, you know, the number top 16s they are the really frequently occurred angles. So I cannot, because for each pair, they are different. So, so there is, yeah, it's in my paper, in appendix, you know, you have all that information, which are for each pair, though, which are top, you know, 16 frequently occurred angles. So whatever that is, you know, so these are actually comes out of that regression, you know, linear regression model, this 0.09. So this is the model.
Okay, good. Now, Renee has included a link in the chat box here to an article in the journal Nature entitled "The Moon's Pull Can Trigger Big Earthquakes." So there's a published article for what it's worth, and she's put the link there in the chat.
Okay, okay.
And then, yeah.
I mean, intuitively, I can think that when Moon is very closer to the Earth, you know, which, you know, happens, we get those, and especially around the full moon. I don't know about the full moon that much, but because I thought that full moon and the new moon, but there is really not, you know, it can also occur any other times too. And so there is some contribution of moon, but there are also contribution of other planets.
Now there's another question from Vincent. He says, the numbers 1, 2, 3, 4, etc. Are they just labels for your angles, or are they harmonics?
No, these are not harmonics. These are actually 16 frequently occurred angles from the training set of data. For example, Pluto, Neptune, they may be, you know, I mean, yeah, they're between 0 and 180.
Okay, and Linda's asking a similar question. She's saying, are the angles 1/16 of 360, 2/16 of 360, etc.?
You know, this. I'm using the half degree arc, so these are the whole numbers. So so the maximum number, you know, so it's from 0 to 180.
Okay. Very good.
So 0, 1. So it could be, these are whole numbers basically in the half a degree arc. So that allow me to use the whole number.
All right. Well, we're just at our time limit here. And, you know, Jagdish, I don't think you would be able to mistake the interest that you've generated amongst this group. They obviously want to know a lot more about what you're doing, and I think they're bringing a lot of interesting comments and questions.
I would love to share whatever I know about this. Yeah.
Mm-hmm. Well, again, we're so glad that you were able to share this with us today. It is some really fascinating and important work, and I know for you it's been a lot of work. It's been a labor of love over many, many years, and I think from all of us, we want to congratulate you for hanging in there, because you keep improving the model. You know, and one of the problems we have is people doing these quick exploratory studies and they post them on Facebook, and that's the end of it. But not you. Not you. Yeah.
This is my passion.
Yeah. Yeah. So I want to give you a big thank you on that point alone, really, from all of us. But it was a really wonderful presentation, and I think you're going to be hearing a lot more from these people over the years, because you've really generated a lot of interest here.
Thank you, Courtney.
All right. Thank you so much. We'll be back in 30 minutes.
Thank you,
with
everybody.
Our next speaker. So thank you so much for coming, and I'll see you all in the next session. All right.
Okay.
Yeah, thank you so much, Jagdish. I'm going to cut out, but okay. I hope just, keep coming back to the sessions. We love having you in here, and we'll meet with you tomorrow as well in the Vedic session.
Right, absolutely, yeah.
Yes, and if you want to bring some comments or some PowerPoint or something to show, you can have like 10 minutes, 15 minutes or so to do your little thing, and we'll get into discussions. We're trying to keep it kind of informal, but
okay.
Yeah.
So there are attendees now?
In the room?
Yeah.
There's a few people here. I was just taking care of business with you. Yeah.
Okay. So am I done here? Or I don't understand.
You're done here. I'm about to exit the room. I was just trying to make sure we're on the same page for tomorrow.
Oh, yeah. Absolutely.
Yeah, I cut the recordings off. You're good.
Okay, great. Thanks.
All right. And then, we've got Dennis and